Welcome to lab number 8, investigation 2, and here we're going to take a look at the effect of impulse, momentum, and collisions. We'll start out with activity 2-1. What I'm going to do is I'm going to take a cart and I'm going to push the cart up against a solid object. In this case, it's this clipboard. What I would like you to do is to observe what happens to the plunger. You see this plunger located right here. Watch what happens to the plunger when it hits that solid surface. Okay, I'll do it one more time. And in fact, what I'll do is I'll add some mass to the cart, and it should give you an even bigger effect. So observe what happens to the plunger. Seems like the faster it goes, the deeper the plunger goes. Okay. So we've got that there. So question 2-1, if friction is negligible, what is the net force exerted on the cart just before it starts to collide? The moment it makes contact, it's going to start getting force, but it's essentially very close to nothing. Then question number 2, when is the magnitude of the force on the cart at its maximum? And what we see is when the cart comes to a momentary stop, the plunger is at its maximum compression. About how long does the collision process take? About half a second, less time, several seconds? Very tough to say. It's definitely not even a second. It's very short. Now, prediction 2-1. Remembering what you observed, attempt a rough sketch of the shape of the force the wall exerts on the cart as a function of time during the collision. Now, during the collision, the force is not constant. To measure the impulse and compare it to the change in momentum of the cart, you've got to first plot a force time graph and find the area under it. And you must also measure the velocity of the cart before and after the collision with the wall. Fortunately, with the computer, we're able to do all of this. Okay, we're going to mount the force sensor. It says in the diagram that we're going to mount the force sensor on the cart. We're not. I'm going to mount the force sensor actually on the bumper that I have set up so that the force sensor will be able to, won't move, and I can change the mass of the cart fairly readily. So putting the force sensor in place, I just screwed it in place to hold it there. There we go. And now I can make some changes to the force sensor in order to have a springy collision or a bouncy collision. In fact, to make a springy collision, I actually have a spring. So I can place this spring on the force sensor, and then when the cart strikes the spring, it will bounce off, just like we see here. And in fact, I will add a little bit of mass, and it'll make the math a little bit easier. And so there's the collision that we would see. Okay. Now I am going to have to make some changes here so that we can actually see what happens when the cart runs into the force sensor. First off, in activity 2-2, we're going to try a nearly elastic collision. So in a perfectly elastic collision, the cart should recoil with the same magnitude of momentum it had before. It won't, because there's going to be some loss due to spring. Set up the motion detector. We've got it set up. The ramp is level. The mass of the cart is going to be half a kilogram. So again, the mass of the cart, M, is going to be equal to 0.500 kilograms. All right. Now, let's go ahead and set up for the collision here. So I'm going to need a moment in order to get that done. I now have it set up so that the cart is by the motion sensor at the end of the track. When I give the cart a push, it will start recording when it gets past a certain distance, and it will stop recording in 2 seconds. This will be plenty of time in order to see the force that is applied by the spring onto the cart in order to make the cart bounce. So let's go ahead and start recording and see what happens. All right, and there's our information. Now, let's go ahead and do a little bit of calculation then. Comes the next part. First of all, let me go ahead and zoom. There's the scale. And I'm going to turn off the stats function, both on the cart and on the velocity. And let's take a look at two things. What we see is the cart is coming in at a constant velocity, looks like around 0.6 of a meter per second, and it comes off at a constant velocity, it looks like at about 0.5 meter per second. It looks like there's a certain amount of time that the collision occurs, that the velocity is changing. This is where we have acceleration in the negative direction because we've got that negative slope. If we take a look here in the applied force area, this is the area where the spring is actually in contact with the cart. Okay, so question 2-1, does the shape of the force time graph agree with your prediction 2-1? Does it look like a curve like that? And you can also expand it out and you can see what I'm talking about by expanding it out. A little bit at the beginning, a lot in the middle, a little bit at the end. By the way, this little wiggle wog at the end is the spring vibrating. Okay, question number 8. Use the analysis and statistics features of the software to measure the average velocity of the cart as it approached the wall. So let's go ahead and see what the average velocity is approaching the wall. That means I need to zoom in like that. Going into the wall, the average velocity turned out to be, using the statistics function, the average velocity was 0.69 going in. So 0.69 meters per second going in. Coming out, the average velocity was, I'll just grab the whole thing and put it there, and it comes out at a velocity of negative 0.42 meters per second. Coming out. This is going to give us a change in velocity of negative 1.11 meter per second. So the next question then is, what is the change in momentum? Well, we can take the momentum going in, multiply it by the momentum coming out, and that will give us the change, that will allow us to calculate the change in momentum. And since the mass is 0.5 kilogram, makes our math a little easier, it becomes, if we divide this by 2, let's see, 1.11, so we're dividing it by 2, so 0.56 kilogram meters per second in the negative direction. Negative 0.56 meters per second. Now comes the fun part. If it's true that the impulse is equal to the change in momentum, then the area underneath our applied force versus time graph should give us the change in momentum. Well, I happen to have a tool to calculate areas, so I'm going to highlight the time of the collision, like so, and then using my area tool, which is here, I click on that, and I get negative 0.57 newtons times seconds. And so what we end up getting is the exact, it's the exact change in momentum. So what are we trying to prove here? That the impulse, force times time, is equal to the change in momentum. Now, of course, we could go ahead and do this again, and I'm going to make a couple of changes here. First off, I'm going to change my calculation there. I'm going to add a term of momentum. And momentum is going to be equal to a mass. And I'm going to call the mass 1 kilogram. And I'm going to multiply that by the velocity. And so what I'm going to do is I'm going to select the velocities. And that's going to give me newtons seconds. Okay? Now, why do I do that? I'll show you. So I'm going to set up the collision again, but this time I'm going to use a full kilogram of mass. So there's 0.75 kilograms, and now here is 1 kilogram. We're going to go ahead and repeat the experiment. Let me turn off these displays here. Okay, and turn off the stats function. Okay, so let's go ahead and do this. We have a new mass of 1 kilogram. We're going to repeat the experiment with the velocity and the time graph. We start recording. There's our collision. We see that the area is minus 0.89 Newton seconds. Now comes the fun part. I can go ahead and use the average velocity. So the first part, the average velocity going into the wall. Oops, excuse me, that's not what I wanted to do. I wanted to do on the velocity graph. The average velocity going into the wall turned out to be the average velocity going into the wall is 0.59 meters per second. The average velocity coming out of the wall is 0.32 meters per second. 4932 is 0.91. We see we had an area of 0.89. Works out pretty nicely. Now here's where I really like using this software, because now I can just go ahead and graph momentum, and we see what the momentum is. The momentum going into the collision was, there we go, it's selected for me. The momentum going into the collision was 0.48 kilogram meters per second. Momentum coming out is 0.32, and that gives us an area of negative 0.90, the impulse of negative 0.90. So as we can see, that for our bouncy collision, impulse certainly does equal to the change in momentum. So I can calculate the impulse two ways. I could try to use the area underneath the force versus time graph, or I can just calculate the change in momentum, the momentum before the collision and the momentum after the collision. Extension 2-4. Answer questions 2.6 and 2.7, okay? And now extension 2-4. What happens on a sticky collision? Well, for a sticky collision, I'm going to replace the spring on the force sensor, and I'm going to replace it with a clay ball holder, and I'm going to have some clay, and the purpose of which is the clay will allow it to stick. Now we're going to keep the 1 kilogram mass on the cart just because I have it preset into the computer. So I need to make the clay and put it in. I've got to shape the clay, get it ready. I have to have it soft. Okay. The question is this impulse momentum true? Is the impulse equal to the change in momentum on a sticky collision as well as on a bouncy collision? So now I'm going to put the clay in place, zero the sensor. Again, we're going to put 1 kilogram of mass, so that makes the math easy. And let's go ahead and see what happens. Prediction 2-3. When the cart hits the wall, it will come to rest stuck to the clay. What do you predict about the impulse? Will it be the same, larger, or smaller than the elastic collision? Is it going to be a bigger impulse when the cart comes to a stop than if the cart bounces? We can see using the, we'll be able to see using the impulse under, whoops. Yes, we'll be able to see with the area under the force versus time graph to find the impulse. So let's go ahead and do the experiment. Okay, so what do we see? We see that the cart came to a stop, just as we expected. We also saw that the impulse is very, very short period of time. But what was the impulse? Let's go ahead and first find the change in the velocity. Well, that was easy to do because the change in velocity is just going to be this area here. And the change in velocity turns out to be minus, I can't read it there because the scale, there it goes, minus 0.5. So the initial velocity is 0.53 meters per second. We're multiplying it by 1 kilogram, so we have a momentum of 0.53 kilogram meters per second. We're going to, the change in velocity, since it's going to 0, means it's negative 0.53. Now let's take a look at the impulse, and we see the impulse on our area is going to be 0.54. There we go. The area is 0.54. And I can actually look at just the area of the impulse itself, area of the collision itself, and we get negative 0.54. So, question 2-8, compare the force time curve for the inelastic collision to that of the nearly elastic collision. How are they similar and how are they different? In both cases, you had a lot of force at the very beginning, a little bit of force, followed by a lot of force, and then it faded away, so it was curved in both cases. But in the first case, with the elastic collision, it lasted longer. Question E2-9, were the impulse and change of momentum equal to each other for the inelastic collision? Yes, they were. E2-10, do you think the momentum change is equal to the impulse for all collisions? Frankly, the answer is yes, they are. So having said that, we will have our discussions about impulse and momentum, how impulse is the transfer of momentum, and how external forces exert and cause impulses, and how external forces change momentum. This concludes lab number 8. So again, if you have any questions, you know how to get a hold of me. Thank you very much and have a good day.